Hello, everyone, and welcome to the pre-lab lecture video for Lab 9, Experiment 5, Observing Chemical Reactions in CHEM 100L. So the objective of this experiment is for students to get some experience performing a variety of chemical reactions. Students are going to identify the signs that a chemical reaction has occurred, and then practice writing a balanced chemical equation for each of the reactions with appropriate phases, and also to classify the reaction. So let's talk about some of the signs that a chemical reaction has occurred. There are 5 main signs that a chemical reaction has taken place. You might see that light is released, or that there's a temperature change in the reaction. It could be that the reaction is giving off heat in the form of increased temperature, or that the reaction actually absorbs heat and the flask gets colder. We can have production of a gas as a sign of a chemical reaction, as well as the formation of a precipitate. A precipitate is a solid that forms in a reaction. And we can also see a color change. Let's watch a video about the signs of a chemical reaction.
Take a breath. Did you know that when you breathe, a chemical reaction takes place? When you eat, chemical reactions break down the food to provide energy and nutrients. Chemical reactions are happening around us all the time. But substances can change without a chemical reaction, like ice melting into liquid water or sugar dissolving in a cup of coffee. So how do you know if a chemical reaction has taken place? We need to look at how substances change for signs of chemical reactions. Chemical reactions cause atoms of the same or different elements to rearrange to form a new substance or substances. The differences between reactants and products indicate that a chemical reaction has taken place. Some common indicators to look for include a color change, formation of precipitate or gases, and a change of temperature. What types of chemical reactions can cause these signs? There are 5 main types of chemical reactions. These reactions include single displacement, double displacement, which includes acid-base reactions, synthesis, decomposition, and combustion. What are the signs of these chemical reactions? First, a single displacement reaction occurs when one element exchanges with another element in a compound. The general form of a single displacement reaction is A plus BC goes to AC plus B. A has changed place with B. An example of a single displacement reaction occurs when a copper wire is suspended in a solution of silver nitrate. The copper displaces the silver, which forms thin crystals of silver precipitate, while the solution turns blue due to the copper nitrate. The signs of this single displacement chemical reaction include the formation of a precipitate as crystals and a change in color. In contrast, during a double displacement reaction, the cations and anions of 2 different molecules trade places. This reaction forms 2 different compounds. The general form of a double displacement reaction is AB plus CD goes to AD plus CB. In this case, A has traded places with C, and B has traded places with D. For example, acid rain is sulfurous acid formed when atmospheric sulfur dioxide combines with water. When acid rain falls on marble, the marble is dissolved. The products are calcium sulfate, a white solid, water, and carbon dioxide. This is an acid-based reaction, which is a special case of the double displacement reaction. The signs this is a chemical reaction are the production of heat and the formation of bubbles as carbon dioxide is given off. Many double displacement reactions result in the formation of a solid, insoluble precipitate. A synthesis reaction occurs when simple reactants form more complicated products. These reactions are in the general form A plus B goes to AB. For example, when molten sodium is put into a container of chlorine gas, it burns with a yellow flame. In this case, signs of a chemical reaction include a temperature change, since the reaction gives off heat. In addition, a white solid, NaCl, a new compound, which you know as table salt, or sodium chloride, is formed. When burning magnesium is put into oxygen, it burns with a bright flame, so a temperature rise is observed. You encounter combustion reactions when hydrocarbons are burned, such as wax or natural gas. Also, when you eat sugar and candy, it is metabolized in your body by a combustion reaction, producing water, carbon dioxide, and heat.
All right, so I wanted to follow that up with talking about some signs that can be a little bit tricky, because you might think that they indicate a chemical reaction has occurred, but actually that's not the case in some of these cases. So let's talk about some of these tricky things that you might see. For example, in this first case, two clear solutions are mixed, and we see that it looks like there's a color change because it used to be clear and now there's some white stuff, right? But we wouldn't consider this a color change. This is actually a precipitate forming. The precipitate is very, very fine particles, and that's why it doesn't initially just settle at the bottom, although very likely if you left this sitting for a while, the white precipitate would eventually settle at the bottom of the flask. So even if it looks like it's mixed around or looks like it's dissolved, it's not dissolved. It's just a fine suspension of a solid that just hasn't settled yet. So that's actually not a color change, but a precipitate. And then not just because you see bubbles doesn't mean that there's necessarily a reaction that has taken place. Because if you're heating something and it's volatile, like for example, this could be a pot of water, right? If you heat it long enough, then the water starts to evaporate. And when it does so, the water, right, is turning into a gas and we see bubbles forming. That is not an indication of a chemical change because the water is just changing from a liquid phase to a gas phase. So that's a physical change, not a chemical change, because you're heating the water. You might say that as we mix this yellow and blue solution, we get a green solution, and that's a color change. But this isn't necessarily because of a chemical reaction. As we know, if we mix a yellow substance and a blue substance, as they combine, we could see a green color. That is not the indication of a chemical reaction. And then the last one that's kind of tricky, and it's tricky because you don't see the change with your eyes, is a change in temperature. So you could be looking at a flask and not notice any change. But if you were to touch the flask, you might notice that the flask is getting hot or getting cold, right? So that would be an indication of a chemical change, but it's a little bit tricky because if you're not touching it, you may not notice that change. All right, let's talk about the reactions that you're going to do in this week's experiment. Reaction A is called oxidation of copper by air to produce copper 2 oxide. So you're going to take some copper bullets, I believe they're called, and put them in your evaporating dish. And you can either put this on your alcohol burner or even directly on your stove to heat it and observe what happens to the copper. When you're writing your reaction, you want to start with copper metal, which is solid, right? React it with air, so it's specifically reacting with the oxygen or the O2 in the air to produce copper 2 oxide. So that's copper 2 plus ions, and oxide is O2 minus ions, right? So put those together to make copper 2 oxide. And then I want you to observe the reaction, right, to, of course, state the what did you notice to indicate the chemical reaction is taking place. Reaction B is the combination of calcium oxide, which is also known as lime water, with carbon dioxide to produce calcium carbonate. So in this case, we're going to take lime water, and you're going to use a straw to blow into the liquid. Be careful to blow into the liquid and not suck the liquid into your mouth. That's an important safety precaution that you want to pay attention to. So as you're blowing into the liquid, you're providing carbon dioxide into the solution, and that is reacting with the calcium oxide to form calcium carbonate. And as always, you're going to do that and note what indication, which of the 5 indications you saw that indicated a chemical reaction was taking place. Reaction C is decomposition of water into hydrogen gas and oxygen gas. To observe this, we're going to place a 9-volt battery into a solution of salt water. The salt in the water is just used to help the battery conduct electrons and is not part of the chemical equation. So the chemical equation that you're going to write starts with water as a liquid and turning into hydrogen gas and oxygen gas. Make sure you're writing H2 and O2 because those are the elemental forms of hydrogen and oxygen. So as you do this, observe what's happening to indicate the presence of a reaction. Reaction D is going to be the combustion of sucrose. To do this, you're going to take a spoon and heat some sugar over your alcohol burner and watch what happens. Remember that combustion uses oxygen from the air. So we're going to take C12H22O11, which is sucrose, combine that with oxygen from the air to produce water vapor. So you can write water is in the gas phase, and carbon dioxide gas. Of course, as in all of these reactions, make sure that you're balancing the molecular reaction. And make sure that for this part of the experiment, you carry out this procedure in a well-ventilated area. For reaction E, we're going to look at the combustion of ethanol. Ethanol can be written as C2H5OH. Remember that all combustion reactions combine the substance with oxygen to produce carbon dioxide gas and water vapor. To do the experiment, you're going to pour a small amount of ethanol onto a spoon and use your alcohol burner to ignite the ethanol. Once the ethanol starts to burn, you don't need any further external heating, so you can move the spoon away from the alcohol burner and watch what happens to the ethanol during the reaction. And because you are heating this one, again, we're going to carry out this procedure in a well-ventilated area. For reaction F, we're going to react some magnesium metal in the form of a magnesium strip with acetic acid. And in the lab previously, we used hydrochloric acid. But since you guys are doing this experiment at home, instead of HCl, we're going to be using acetic acid, which is a weaker acid. It's still going to produce hydrogen gas, and instead of magnesium chloride, we're going to form magnesium acetate. So to do this, we're going to place a magnesium strip into a solution of acetic acid and observe what happens. For part 2, we're going to place the magnesium strip into water, which we're going to heat with the alcohol burner. And we're going to add a drop or 2 of phenolphthalein indicator, which turns pink if hydroxide forms. So note what happens and whether or not any hydroxide forms in that reaction. So as soon as we get to this part, it's going to ask us, the activity or experiment was going to ask us to start writing different types of equations. Previously, we've always been writing our balanced molecular equation, but now we're going to also practice writing what is called a total or complete ionic equation and also a net ionic equation. So the balanced molecular equation, right, includes the molecules or formula units involved in the reaction. So for example, we can see that barium nitrate is being reacted with nickel sulfate to form nickel nitrate and solid barium sulfate. So notice that the states of matter are included along with the balanced chemical equation. To turn this into the complete or total ionic equation, we're going to separate ions in solution. So anything that is labeled as aqueous can be separated into its constituent ions. So instead of writing barium nitrate, we're going to separate that into barium ions and nitrate ions. Because there are 2 nitrate ions needed to balance the barium ion, we're going to go ahead and change this 2 into a coefficient to note that we have 2 nitrates balancing the 1 barium ion. Nickel sulfate is also in an aqueous solution, so we're going to separate that into nickel 2+ ions and sulfate ions. And that forms, again, nickel ions in the product side and nitrate ions, 2 of them, and barium sulfate. Because barium sulfate precipitates from this reaction, it's in the solid phase and we do not separate it into ions. Then we can convert the complete or total ionic equation into the net ionic equation. In the net ionic equation, we eliminate spectator ions. Spectator ions are ions that do not react. Essentially, they exist on both the reactants and the product side unchanged. So because they did not change, we say they spectate or watch the ions that do change. And so anything that remains unchanged on the reactants and product side can be canceled out. And then we have the net ionic equation, which just shows us the actual chemical change, which are that barium ions and sulfate ions are combining to form solid barium sulfate. So let's see how the writing of these different types of equations would apply to a similar reaction to the one that you're doing in this experiment. Notice that I've chosen here the reaction of magnesium solid with hydrochloric acid. So again, we are actually going to be using acetic acid instead of hydrochloric acid. But the reaction is very similar because hydrochloric acid separates into hydrogen ions, or H+, and chloride ions. And acetic acid separates into hydrogen ions and acetate ions. So the only difference is whether or not there's chloride ions or acetate ions in solution. The products are going to be the magnesium chloride, which is going to be dissolved, and hydrogen gas. So the first equation that you see here is the balanced molecular equation. Notice that everything that's involved in all of the reaction species, right, are the molecules or formula units are seen, as well as the phases and any coefficients to balance the reaction. Then we convert that into the total ionic equation, sometimes called the complete ionic equation. Remember that anything in aqueous solution is separated into its constituent ions. So hydrochloric acid, for example, is separated into H+ ions and chloride ions, making sure to indicate that there are 2 of each because we still want to have the equation balanced. And in the products, we have magnesium ions, chloride ions, and hydrogen gas. Next, we look to see if there are any spectator ions. Again, those are ions that do not change, that exist the same on both the products and reactant side. So what we might notice here that there's 2 chloride ions on the right and the reactant side, and 2 chloride ions on the product side. So those are spectator ions because they have not changed. We can eliminate those when we write the net ionic equation. The magnesium has changed though, because it's gone from magnesium solid to magnesium 2+ ions. Those are different, and so those do not cancel out. In addition, H+ ions have converted to hydrogen gas, which represents a chemical change. So leaving out the chloride spectator ions, we come up with this net ionic equation. Again, this one, right, is going to be, the last equation is actually the same. The only difference with what you're doing is that you will have acetate instead of chloride. The last reaction is reaction G, which is the reaction of solid baking soda with vinegar, which is a dilute solution of acetic acid. So in this reaction, we're adding solid sodium bicarbonate, which is baking soda, but initially it is going to dissolve before it reacts. So I don't want you to write solid sodium bicarbonate. Go ahead and write it as aqueous, because even though you've added a solid, the vinegar is mostly water. So it's going to dissolve in that water and then react. So we're going to have the phase be aqueous. In addition, the acetic acid is also aqueous. And then the products of this reaction are sodium acetate, water, and carbon dioxide gas. So initially, a double displacement reaction is occurring when the sodium ions and the hydrogen ions switch places. The sodium ions are provided from sodium bicarbonate. So this breaks apart into sodium ions and bicarbonate ions. Acetic acid will also dissociate. H+ will separate from acetate ion. So you can see that as H+ and Na+ switch places, we end up with H2CO3 and sodium acetate. The sodium acetate remains as it is, but H2CO3, which is hydrogen carbonate, is not stable, and it decomposes into water and carbon dioxide gas. So initially in this reaction, we're having a double displacement and then followed by a decomposition. All right, that was actually a very quick video, and let me know as always if you guys have any questions this week.